Much like a laptop computer, the Raspberry Pi Pico has several ports called GPIO pins that can be connected to various hardware peripherals like an LCD display or a temperature sensor. Also like a laptop computer, there are only a limited number of pins for each type of connection. For example, the Pico only supports the connection of two UART-based devices, but what if we wanted to connect more than two? There are so many other GPIO pins available. What if we could take any one of those pins and turn them into a UART port? Well, good news. We can do just that with the Pico's programmable I/O feature. On a very basic level, connecting to an external device is nothing more than sending a bunch of zeros and ones via cable, which can be visualized like a pulse signal that goes either high or low. We can use software to manipulate the signal of any GPIO pin to go up and down with special timings, mimicking the communication protocol that the external device uses. This is known as bit bagging, and it's a very CPU-intensive process because of the strict timing requirements. To solve this, the Pico has two mini processors that run independently from the main CPU. They're called programmable I/O cores that are tuned especially to perform bit bagging operations with full access to all of the Pico's GPIO pins. Here's a simple view of what a PIO core looks like. In the center, we have a state machine which, once activated, keeps waiting for incoming data and processes it immediately when it arrives. The data can come from two places. It can come from our main program, or it can come from a GPIO pin. To define what our state machine does, we need to write a special PIO program written in a special language called PIO assembly. It consists of 9 commands, which may seem simple, but can in fact be used to do very complex operations. To illustrate, I'll use a simple example of adding a new UART transmission port, which can transmit data to a UART-based device. In our main program, we'll do some initialization work to set up the PIO core. We first define which GPIO pins the PIO core has access to. First, there's the out pin. Whenever we use the PIO command out, this is the pin that will output the signal to. Then there's the side set pin. Every time the PIO core executes an instruction, it can simultaneously change the signal of a GPIO pin. So it can effectively do two things in a single clock cycle. This is called side setting, because we're setting a GPIO pin on the side. So whatever GPIO pin we set as the side set pin, every time we execute a side set using the command side 0 or 1, that pin signal will be modified. Let's set both pins to be GPIO number 27, which usually isn't used for UART transmissions. There are other pins we can set, but for this simple tutorial, we'll just set the out and side set pins. Afterwards, our main program will load the PIO program onto the state machine and then activate it. Once the state machine is running, our main program can read from and write data to the PIO core. Now let's start writing our PIO program. Whenever our main program sends data to the PIO core, it gets stored in the transmission FIFO. For this example, let's say we want to transmit the value 180, which in binary is 1011000100. The first line of our PIO program will be pull. This command will pull data from the transmission FIFO into the state machine's output shift register. Since we're about to begin a UART transmission, we need to send a start signal to indicate that the transmission is about to start. This is done by pulling the GPIO's signal from high to low for about 8 cycles. But in order to do a pull down, the signal needs to be high to begin with, so we'll first pull it high. With side setting, we can drive our GPIO pin high concurrently with the pull operation by adding the command side 1. Finally, we delay for 7 cycles. This is because every PIO instruction takes 1 clock cycle to finish. So to ensure that the GPIO pin is driven high for 8 cycles, we need to delay by an additional 7 cycles. Now that the GPIO pin has been driven high, we can now drive it low for another 8 cycles to indicate that the transmission is about to start. We also want to prepare a loop counter because we're going to use an 8 iteration loop to output 8 bits of data. Once again, with side setting, we can do both operations at the same time. First, we store the number 7 in Scratch Register X with setX7. Scratch registers X and Y are used to store temporary variables. They're called Scratch registers because they're like the scratch paper you use when you're doing math. Then we'll set the GPIO pin to be driven low. We'll delay for 7 cycles to ensure that the start signal is asserted for a full 8 cycles because remember, a PIO instruction itself takes 1 cycle to complete. Now that our start signal is complete, we can start sending data. First, we have a code label, bit loop, which we'll use to mark the start of our loop, giving us a place to jump back to at the end of each loop. Now for the loop itself. First, we use the out command to shift 1 bit from the output shift register to our GPIO pin. Since the first bit of data we want to send is 1, this will drive the GPIO signal high. Then we prepare to jump back to the beginning of the loop. We'll first check if the loop counter in Scratch Register X is equal to 0. If not, then we'll decrease it by 1 to indicate that 1 iteration is completed, and then prepare to jump back to bit loop, back to the start of our loop. But we can't jump back just yet because for each bit of data, we need to hold the signal for a total of 8 cycles. Since the 2 commands, out and jump, both take up 2 clock cycles, we need to delay an additional 6 cycles. After the 6 cycles are over, the state machine will jump back to the bit loop label, back to the start of the loop. For the next 7 bits of data, the process keeps repeating with each bit of data being outputted to the GPIO pin until the jump command evaluates the loop counter in Scratch Register X and finds it to be equal to 0. In that case, the loop stops, and the program will automatically jump back to the very first command, which was pull sideset 1, delay 7. The thing about the pull command is that if the transmission FIFO is empty, then it just waits until there's something to be read, so the state machine effectively returns to a waiting state. The process for programming a UART receive pin is quite similar. The difference is that we use the in command to shift bits of input data from the GPIO pin into the input shift register, and then use the push command to push that data into the receive FIFO, where the main program can access it. For the full implementation, with detailed written explanations, please refer to the official documentation links in the description. This was just meant to give you a visual representation of what's happening with basic PIO assembly code. Thanks for watching.